Okay, now that we've written vectors in component form, let's look at how to add vectors again. So let's say you want to add vector A and B to get vector R. A and B to get vector R. There's the graphical method of adding vectors. Now this doesn't work that great in practice. It's good to have a picture, but here's A in terms of its components, AXI plus AYJ. And here's B in terms of its components. And now here are the rules for adding vectors in component form. You just add the components together. So the component of x component of r would be just the sum of the two components, and you add the two y components together. Okay, and so that's how you add vectors. So in fact, this can be generalized to if r were equal to a plus 3b plus c or minus c, so you get the idea. This would be ax plus 3x, 3bx minus cxi, that would be the x component, plus ay plus 3by minus cyj. Alright, so vector addition becomes real simple. Now, laws of physics are expressed as equations, okay? And so if you have an equation, here's the basic rule. Just like it has to have the same dimension on the left-hand side as the right-hand side, it should have the same type of mathematical quantity. You can't have a scalar on the left-hand side and vectors on the right-hand side. So for an equation to be true, if you have a vector on the left-hand side, you have to have vectors on the right-hand side. So this is a vector, that's a vector. This is a vector times a scalar, which is a vector. This is a scalar times a vector times a scalar, which is a vector. And the sum of three vectors is equal to that vector. And here's another thing we learned from dimensional analysis. This is a position vector, so it has dimensions of length. Okay, so this term has to have dimensions of length. This term has to have dimensions of length. This term has to have dimensions of length. Okay. Here's another equation, law of physics. This is the famous Einstein equation from general relativity. What this does is it relates the curvature of space-time to the distribution of matter and energy. These are tensors. Okay. These are, so you can think of them as matrices. So anyway, these are two-dimensional, these are tensors, and so you see each one is a has two indices. This tensor has two indices, this tensor has two indices, and this tensor has two indices. This is really 16 equations. Each of these tensors has 16 components, and so this is really 16 equations. All right. Now the last thing we'll learn is how to multiply vectors. Okay, so it turns out when you were multiplying numbers, there was only one way to multiply numbers. 5 times 4 was 20, and but when you're multiplying vectors, you can define two useful products, two different kinds of useful products. We'll define something called a dot product or a scalar product or dot product. And as the name suggests, as the name suggests, the result is a scalar. So here's the definition of scalar product, dot product. You're taking the product of vector A and B, and the notation is A dot B, and it's defined as the sum is equal to the magnitude of A times the magnitude of B times the cosine of the angle between the two. And the angle the angle between the two is when they're drawn from the same point. So this angle can be anything from 0 to 180 degrees. Okay, so When the angle is less than 90 degrees, that's positive, this is positive, this is positive, this is positive. So the dot product is positive. When this angle is greater than 90 degrees, cosine phi is negative and the dot product is negative. Okay, so that's how we define the dot product. Here's the dot product written in terms of components, okay, in terms of the x and y components. And so in fact, you can actually use this equation to find the angle between the two vectors. Okay. All right, so that's the first way of multiplying vectors. And now we'll define the second way of useful way of multiplying vectors, the vector product. As the name suggests, the result is a vector. Okay. So here will be the notation. We're trying to multiply vector A and B. The result is going to be C. We'll call it C. And here is the magnitude. So here's vector A, here's vector B, and that's the angle between the two vectors A and B that you're trying to multiply. The angle between the two. Now, I've used phi here. The diagram shows phi, theta, but they're the same. That's meant to be the same angle. Okay. Now here is the cross product. It's also called the cross product in terms of components. So the vector C is given by AYBZ minus BYAZI, AZBX minus AXBZJ, AXBY minus AYBXK. So there is the cross product. And unlike numbers, 4 times 5 is equal to 5 times 4 equal to 20. See, this cross product is what is called anti-commutative. A cross B is the negative of B cross A. So this obviously is not like scalar multiplication. Okay. So anyway, here's the will form a plane. Two non-linear collinear vectors will form a plane, and the cross product is perpendicular to that plane. And the direction in which you find the C is in, you use your right hand. If the thumb indicates the first vector and your index finger is the second vector, your middle finger indicates the third vector. Also, and good one to remember is as you turn the first vector into the second vector, the direction in which if you turn a screw from the first vector to the second vector, the direction in which the screw moves would give you the direction of the third vector of the cross product. Alright, so here are the properties of cross product again. A cross B is equal to minus B cross A. A cross B is C. Okay. The magnitude of A cross B is magnitude of AB and times the sine of the angle between the two vectors. Okay. It's very useful to remember the cross product between unit vectors. I cross J is K, J cross K is I, so that's why this circle. K cross I is J. Okay. And so I cross J is K, and of course J cross I is minus K, and so on. Okay. So the cross product of unit vectors are good to remember. Alright, that covers this chapter.